Hello everyone. In this video we will solve this problem of these two masses which are on a surface. The question asks what should be the force such that this mass, small mass which is in contact with the capital mass M does not fall down. So in order for that to happen, there must be some friction between the capital mass M and the small mass m. The friction here is mu2. There is a friction between the capital mass M and the surface on which the object is moving. This friction is mu1. This is the coefficient of kinetic friction. Since this object is not supposed to move, this is the coefficient of static friction. The whole system is moving to the right, and the force applied on the capital mass, this large block, is F. The question asks what should be the minimum force? What should be the minimum force such that the small mass M remains static? Okay. So let's see how we will solve the problem. The problem is actually quite simple. If you just follow the steps properly, it's actually a very simple problem. It's a simple application of Newton's laws. So let's first consider the small mass m. The problem says that the small mass m is static in the y direction, not in the x direction. Of course, the whole thing must be moving in the x direction, but in the y direction it's not moving. So let's see what are the forces on this mass m. This mass is in contact with the larger block M at this surface, and since they are in contact, because of the contact there must be a normal force on this mass M, right? That's the normal force, the contact with the capital mass. So when you push the larger block, this block again pushes the smaller block, and that's why this block moves. There is no direct force acting on this smaller block. So there must be a contact force between these two objects which causes the small block to move. So let's write down, let's call this contact force N2. Okay, so N2 is the contact force on this mass M. Because of this contact force, this object moves in the x direction, and let's call this acceleration of the smaller block A. We will call this acceleration A. Now, since this mass is in normal gravitational field, it would experience a downward force mg, and because there is some friction between these two blocks, there would be a frictional force between the two objects, and the frictional force would be mu2 n2, where mu2, remember, is the coefficient of static friction between the two blocks. Now we have to find out what is the minimum force that must be applied so that this system stays in the static in the y direction. For that, the minimum force that must be applied must be such that mu2 n2, or the frictional force along the y direction upwards, must be larger than mg. Okay, that's so you have to apply a force such that this frictional force is larger than the force mg, gravity acting downwards. And if you want the minimum force, then it should be such that the difference between these two things must be equal to 0. Okay, that is our y direction. Y direction. Now what happens in the x direction? X direction. Now in the x direction there is an acceleration on the object, and the acceleration is ma. So let's write down the mass times the acceleration. That must be equal to the net force in the x direction. Now what is the net force in the x direction? It's simply n2, right? The net force in the x direction is n2, which causes the acceleration mass times a. Now we can use this mass times A, this equation and this equation to find out a relationship between the acceleration of the entire object and the acceleration due to gravity and mu2, because these are the quantities that we know. N2 is something that we don't know or we don't care about. So let's substitute the value of N2 in this equation, in the first equation. If we do that, we get mu2 ma minus mg equals 0. If you solve this, you will get A equals mg over mu2m, which is equal to g over mu2. So that is the acceleration that must be applied to this object in order to make sure that it does not move in the y direction. Okay, so remember that the acceleration for the object must be equal to g over mu2. Now let's consider what are the different forces on the larger block M. Remember that the larger block M is being pushed from this side with a force F. It must have again the gravitational force mg. Since it is being pushed, there is some motion in this object. That motion must cause some frictional, the kinetic friction here. This kinetic friction should be equal to mu1 times the normal force on this object. Now what is the normal force? We don't know yet. So let's just call this normal force N1. On top of that, we know that this object again is in contact with the smaller object, and because they are in contact, they have a contact force. That contact force we called earlier, we called it N2. And then there must be a frictional force because there is friction between the two objects, and the frictional coefficient again here was mu2, and because the normal force is N2, the frictional force, which would act downwards, would be mu2 N2. So now these are the different forces acting on this mass M. So once we know all the forces, we can write down now the Newton's equations. So let's first write down the Newton's equation in the y direction again. Y direction. Again, we know that in the y direction there is no acceleration. This object is not moving in the y direction. So the acceleration in the y direction is 0, which means that AY is equal to 0, which means that if we write mass times acceleration in the y direction, this should be equal to the net force in the y direction, right? But mass times acceleration is equal to 0, so we should get 0 equals the net force in the y direction. Now what is the net force in the y direction? It must be equal to N1, this force, which is positive upwards, minus mg minus mu2 N2. So these are the different forces acting on the y direction. We can do a little bit more simplification. We can write N1 equals mg minus mu2 N2, plus, and then remember that mu2 N2, if you go back, mu2 N2 was equal to mg, right? Mu2 N2 minus mg was equal to 0. So mu2 N2 must be equal to mg. So we can write here capital M. This must be capital M. Capital M, capital Mg plus small mg, or capital M plus small m times g. That's the value of the normal force on this object, on the larger object. Now once we know the normal force, we can write down the forces in the x direction, x direction. Now remember, in the x direction, the acceleration is a, which is equal to g over mu 2. That's the acceleration with which the whole system is moving towards the right direction. So we must have mass times the acceleration equal to the net force. Now what is the net force in the x direction? We have capital F, which is in the positive x direction. We have minus N2, this force here, the normal force due to this smaller object, the contact between the larger object and the smaller object. And we have the frictional force mu1 N1 minus mu1 N1. Okay, now let me write it. Let me take both these. We are interested in the force F, and to find out the force F, we will write F equals ma plus N2. So we are taking N2 in the other side, and mu1 N1 plus mu1 N1. Now, rest of the problem is very simple. What you do is, in place of this acceleration, you put g over mu 2. In place of n2, remember again, we can write, in place of n2, we can write mg over mu 2, or ma. We can write n2 as ma. So let's do that. So we can write capital M A plus small m a, n2 is equal to small m a, plus mu1 times n1, but n1 is capital M plus small mg. So this would be mu1 capital M plus small m g. Okay, now the rest of it is something very simple. Let me write this down on the next page. So if you remember, the F equals capital M plus small m a plus mu1 times capital M plus small m g. For acceleration A, we had A was equal to g over mu 2. So we can write this as capital M plus small m g over mu 2 plus mu1 capital M capital M plus small m g. And if you do further simplification, you can see that F can be written as capital M plus small m g into mu1 plus 1 over mu 2. So that is the solution. That is the minimum force which is required in order to make sure that this object does not fall downwards. Now we can check whether this is true or not. Let's say that there was no friction between these two objects. If there was no friction, so if mu 2 was equal to 0, then we can see that f goes to infinity, right? Because mu2 is in the denominator here, which means that you need infinite amount of force to keep this object from falling down, or essentially whatever you do, this object is not going to stay static. It's going to fall down in the y direction, which means that you need at least some amount of friction to keep this object static. So mu2 cannot be equal to 0 in order to keep this object static. So this physically makes sense. You can also see that it doesn't matter whether you have friction between this capital mass, the bigger mass, and this surface or not. Even if this term was equal to 0, it's still possible to have a situation where the smaller mass remains static as long as there is some friction between the two blocks. Okay, so I hope you are able to solve this problem. You understand this. It's kind of very simple. You just write down the forces in both the direction and be careful about identifying what the forces are. And once you have identified it, you just write down the Newton's equation and solve them, and you are essentially done. So if you like this video, give me a like, a thumbs up, subscribe to the channel, and if you have other questions, write down in the comment box, and I would be happy to solve other problems. This was an interesting problem. See you in the next video. Thank you.